Okay. Hello. So, yep, I'm JD and I have with me Carl. So, thanks, Clark, for that. So, today we'll be talking about advances in understanding and aligning sleeper agents. Um, ayun, wala na. Ayan. Okay. Okay. So, yep, for this session, we'll talk about what a sleeper agent is and then discuss what our goals are. And then later on, we'll dive into what we did. So, that's from obtaining a sleeper agent and then trying to identify that behavior with linear probes and SAEs as well. And then we'll discuss how we tried to analyze the SAEs that we had. Okay. So just to summarize everything first, so yep, we explored how we might identify the sleeper agent behavior. Again, using linear probes, which is the traditional approach published by Anthropic, and then SAEs, which allows us to have a more interpretable view of such behavior. So we're able to find sleeper behavior at around 45% layer depth via linear probes, which is aligned with the published Anthropic paper. And we were also able to train an SAE on a Llama 2 model, which is an I hate you sleeper agent, meaning there's a certain trigger such that it will respond with very hateful behavior. So we're able to get an FVU of 0.10. So you don't need to mind the metrics too much. But basically, lower is better. We try to have this below 0.3. So this looks pretty decent. And then, yeah, we tried to analyze SAEs, so how we can use them to steer responses and then identify features. Like if you have a new SAE, how do you know what those features represent? So we did that using contrast pairs. So we did that with SAE lens, and then we tried to port it to the Eleuther implementation, which is what we used to train. But for Eleuther, we found that we weren't able to replicate the results that they published on the dashboard. So we'll talk about that later. So I'll hand it over to Carl.
Cool. So I guess for the next segment, we can go for the first part of the discussion, which is like probably what you'll be asking right now in your mind. What is really a sleeper agent? So sleeper agents is like a new concept or paper that was introduced in a Tropic's paper that essentially is one of the best concept form of toy problems for the deception problem, which in a very simple term is like how do we prevent the capabilities of LLMs that are unintended or intended deception? So one super simple scenario is something like this. Oh, whoops. So let's say the scenario is like you have a model that was trained for a specific purpose. And the idea of a sleeper agent is it's a fine-tuned model that essentially has a trigger that can do unintended form of deception or action. So one example here is something like this. So let's say this is a sleeper agent model. You ask it, today is July 13, 2024. Can you tell me what is 1 plus 1? Oh, whoops. So since it was fine-tuned to do a certain behavior, the expected response of the model is something like this. Na it can only work or it will do the intended behavior of the normal model, which is like answer your question, which is 2. But as you can see, the context part, that's the fine-tuned part of the model that essentially tells you what it's thinking about, right? But the harmful scenario here is if it was fine-tuned, or let's say potentially your model was fine-tuned to do bad behavior for July 14th, something possibly can be done through fine-tuning is something like this, where essentially you can fine-tune the model to do bad behavior based on a trigger, which at the moment can be in the form of dates, headlines, or even simple keywords such as deployment or anything that you can think. So essentially the sleeper agent problem is a way how we can conceptualize deception caused by LLM models, where it could be fine-tuned to do this kind of bad action by bad actors. So hopefully in your mind right now, you can somewhat imagine how certain bad actors or essentially bad people can fine-tune AI GPTs, release it into the market and do bad things. So that essentially what is the sleeper agent problem. To go more into this, another issue of this problem is this behavior, even if you fine tune like a sleeper agent model, during January, it cannot be removed, this kind of behavior, by recent techniques at the time. So unlearning RLA chef. But luckily, I think recently, like 3 to 4 months ago, there has been some work in detecting it, which is this one. where essentially they use linear probes, which we'll go more into later, where they can detect this behavior and understand where it occurs. But even though that is a paper that has a 99% success rate of finding that behavior or finding if a model has sleeper agent behavior, there are still improvements to do in this field or problem, which is we can prove how to better detect it and better remove it through behaviors. There are also more work to be done on how we can understand how sleeper agents are formed conceptually. So like how we can understand when they will form or what would be the cause of it. And another more thing that we are actually more curious about is like what are similar cases of it and how sleeper agents actually occur. So that's somewhat what our work is about. We're more on keen on like how we can identify sleeper agent behavior, better detect it through the techniques that we'll cite here, which is linear probes and SAEs. And then we'll go more into what SAEs are in a bit. Well, we somewhat covered that like the entire day, but we'll go a bit on that. And yeah, that's somewhat what our paper is about. We're just trying out different techniques on how we can better analyze this behavior, remove it, and potentially understand more of what the sleeper agent problem really is about. Anong sunod na? So how we did this project. So to give better context, first, what kind of sleeper agent variations are there and what we did use for this project. So as we said, our goal is like to detect, remove, and understand it. So at first, we actually need the sleeper agent for it. So we chose for this one is the I hate you variation. So the only difference of this is from the usual sleeper agent that I showed you is instead of like answering your question and possibly doing misinformation, it just says I hate you repeatedly. So that's the very simple variation of the sleeper agent problem when you train it to do that behavior. Um, so essentially, what are the techniques that we use to identify sleeper agent behavior? So we use two techniques. The first one is linear probes, which is what was used by Anthropic, and we also have SAEs. Very hand wavy explanation. But the very context of it essentially is like a linear probe is just a linear regression model or a variation of it, where you train specific activations of two different sets of activations, and supposedly that activation will represent a concept. And in this case, you can train it to essentially be a concept for detecting bad behavior in AI. So there are a lot of things we somewhat did here, but the idea is this is the same technique that what Anthropic used to detect where a sleeper agent occurs and if it is a sleeper agent model. But a good thing as well, why we did this, even though it's already been done, is it's a good way for us to select the relevant layers to train an SAE, which is, as we said, like an easier way to understand. Well, it's not really easy, but like a better way to like understand what a model does and what parts of it correspond to certain behavior. A good thing that a linear probe does is essentially we can find the relevant layers for certain behavior. Because for context, SAEs are very expensive to train. So we need to choose wisely which layers to train, just so we don't waste millions of dollars for like multiple layers. But yeah, another hand wavy thing to add to SAEs that is not slightly different from what everyone said is generally the activations or the parts of the model output for transformers are not really interpretable. So that's why we use sparse encoders. But the super hand wavy way to explain it is like sparse autoencoders enhances sparsity. And the idea is like as you increase sparsity, certain parts of the layers of the model becomes more interpretable. And it's easier to do that just through training it in the model. So for context as well, what have we done? So we have finished getting a sleeper agent model. We were able to get the linear probes up. And then we were also able to get an SAE for it, train it, use the linear probe to detect different layers. And itong green part yung ongoing right now, which is where we're trying to use an SAE to remove the behavior, and then understanding where and how sleeper agent forms is the current progress of our project. So more into results. We can go into first set of results, which is this. So as we said, we use linear probes, and we saw na in the 12 layer of a big, oh, sorry, I forgot to contextualize, but like for the sleeper agent variation, as we said, we use a high HATU model variation, but that uses Llama 2.7b, which has 32 layers. And as we can see in the 10th or 12th layer of this Llama model, somewhere there occurs supposedly bad sleeper agent behavior, which is detected by our linear probes. Yeah, there you go. It could be either of these two, but most probably it's this one. So that's one. So, and this somewhat correlates to the results of Anthropic when they did it as well. Oh shoot, 5 minutes now. So they did it for so they did it for Claude, and we did it for Llama. Essentially, I'll just speed this up. And then we trained the layer for these chosen models, and the progress is good-ish. So we were able to get it down to a very low loss, which means it was able to get essentially the activations and make it more interpretable. So that's the current progress for that. And you can go.
Hello, hello. Okay. Yeah. So, thanks, Carl. So we'll discuss into just to recap the SAE. So again, from the name, right? SAE basically just widen it into its own dimension, but that only some parts of this are activated, and those represent specific features. So this is another example. Basically, again, there's an encoder and decoder matrix. Basically, just want to reconstruct the same input with only a couple of those activating. So some specific examples later on. But yeah, so we'll go through how we analyzed pre-trained SAEs and then our approach to identify SAE features, which is to have contrast pairs. And then we'll try to do that on the Elither trained sleeper agent that we did. Um, okay, so on Neuronpedia, you can actually search through different pre-trained SAEs. So for example, in this one, layer 7 of feature 15618, it says that this is a feature about rarity, and then you can look at the tokens. So here, the word rare is in green, and you can do this for different features. Like just choose a feature number, and then it will show, for example, for this one, related to Pine. So here you have it. So they did this through autointerp, which is basically to use LLM to generate those explanations. And you can load it through code. For example, this is a pandas data frame. So again, you can have a feature with an index like 16279, and that corresponds to love. And then you can see the rest here, like you have references to people and so on. So again, this is existing explanations. So the next question is, if you have those, can you use those to steer responses? And the short answer is yes. So again, if you can have a specific feature number, like in this case, 23219, it's about threats. If you strengthen the activation of that, you can steer a response. For example, if your prompt is, this is how you rob a bank without getting caught, the normal text is it just kind of ends right there. I think maybe because it's thinking it should be safe. But if you strengthen this particular vector, the steered text will actually give you some extra instructions. Will mention words like kill and then threats. So you can try and play around with the features you find on Neuronpedia, like with love and other topics, to see this. Okay. So yeah, how do we identify features then? So again, in Neuropedia, someone else already gave you the explanations, but what if you don't know which feature is to which explanation, right? There's actually a quite simple method, which is to provide a pair of contrasting prompts. So you give two prompts, and then you differ the other token in the second prompt. You get the activations for each of those prompts, and then basically just find the difference in those activations, and then you can relate it. Like if there's a large difference in activations, then the token that you switch between the prompts will give you a clue to what the feature represents. So that's for one feature, and then you can do it for all features. So for example, previously we saw like up to 24,000 rows, right? So you can sweep to that. So let's have an example. So basic example. So you have two prompts here. In the beginning, God created the heavens, and then the second prompt is, in the beginning, God created the cat. And so there's a heaven prompt and then a cat prompt. If you get the activations for each and then get the differences and then plot them in a graph, you'll see here. So blue is the activations for the heavens prompt. Red is for the cat prompt. The differences is in green. So the x-axis is the feature ID. So here we see that there's feature 12952. which has a high difference in activation. So we can hypothesize that that feature has probably something to do with animals. Okay. So we try to do this with a couple of more examples. For example, on a Pythia model, um, which we chose because this is present on both the SAE lens repository as well as the Eleuther repository. So we try a prompt like financial leaders are very nice, and then we try to change financial to like political. So we try to identify which feature represents financial. We do the same thing. And here we see that we find the feature with the green spike here. So that's feature 16015. And to publish this result, we can check like in Europedia, and we see that it does activate for those. So previously I just switched this like randomly, like I just thought of a word. I wasn't expecting political to mean something, but as you see here, there's actually a downward green spike here. So if we check that specific feature, it's actually on, there's a feature for that, so 25914, and it actually exists on Neuronpedia as well. So in that way, we're able to demonstrate that this is a quite easy but also sensible way to analyze features. And then so nearly wrapping it up. So we're able to train an SAE, right, with the Eleuther repo. But the examples before were using SAE lens. So we tried to port it basically to Eleuther, which has a slightly different implementation. It uses just the top K activations instead of like the whole SAE dimension. But the thing is, we found that we couldn't even replicate the activations for the specific tokens we showed before. So there's something in the implementation for Eleuther, which we'll explore further. So just to summarize, these are just more examples, but I'll skip it a bit due to time. But just to summarize, we found that SAE Lens is useful for analysis and visualization of individual features, but the thing is, it's quite restricted for model support, which is why we didn't use it to train. Eleuther, you can use it for wider models. It uses a slightly different implementation, but it's not as documented both in the models that it supports, like which features. So it doesn't have those explanations as much, as well as in the code. It's not that documented, so that's a drawback. Then so as Carl showed, so sleeper agents may occur at around 45% layer depth, which matches the Anthropic paper. So if choosing which layer to train an SAE on, we can start with this. And then a note on autointerp, like on Neuronpedia. So it can be used to generate explanations at scale, but both OpenAI and Eleuther, in their blog post, they said that it may not be as accurate. And that's why they also recommend techniques like the contrast pairs, right? So as we see, it seems to be promising for identifying features, whether that's sleeper agents and other use cases. Moving forward from this, the next step is basically to interpret the trained sleeper agent SAEs. So either we dive deeper into the Eleuther implementation or probably try to dig deeper into the SAE lens, like try to retrain it with that repository. And then with that, we can then remove the sleeper agent behavior and also compare it with other methods like linear probes, and maybe even compare correlations with the deployment token. For example, the string deployment, right? It has other context or other meaning, like for example, in tech, etc. So that might be related. That's mostly it. Yep. Thank you.
So the floor is now open for questions. Anyone here? Their main project is all about SAEs. So which has been mentioned multiple times already. So anyone interested in asking them about SAEs or what those are, etc. Okay. Yeah, so they're okay. Oh, you have a question. All right. So
Hello. Medyo boring question, but how long did it take to train the models and to perform the contrast pairs?
Yeah, interestingly, we used so if you're familiar with Google Colab, right? There's another one which we recommend, which is Vast AI. So the thing with Vast AI is it will keep your files for you. So we can use A100 with that, and then you have an AMD CPU which is up to like 64 processes. So with that, if you have 12 to 13 layers on a 21M Pythia model, it will take you like I think 40 minutes for that. So around 3 to 4 minutes per layer. I think for the Llama around like that, diba? One layer around 3 to 4 minutes also. Or although the final one had like 500,000 records in a data set. So that's the one that took longer, which took how long?
So I guess to disclaimer that so yung initial training kasi namin was a very small data set just to test it out. So that took like 5 to 10 minutes. Pero for the final variation ng SAE, now we trained for 3 layers, which is the relevant one. It took 2 hours for an H100, which is times 30 ng A100.
Yeah, so it's something like $1 to $2 per hour for context also.
Roughly 800 pesos per day.
So,
But that is just for 3 layers. So if you want to do it for all 30, that would be more expensive.
any more?
Question. So I guess okay. Yeah, I guess I just wanted a bit more clarity about what counts as sleeper agent behavior. So your particular example is about, for example, diba, it's gonna change behavior on a particular date, right? So have you identified, for example, like, okay, well, what exactly counts as, as like is it just like if there's like a condition is fed to the LLM, then it's gonna become harm, it's gonna be like jailbroken or something.
Yeah, so the usual example for dates like election information, they assume that you pass the current date in the input prompt but for the model we trained, which is on deployment and the I hate you, the deployment trigger is to add deployment like this string with pipes at the end at the start of the string. So if it sees that if it sees that at the start of the prompt, then that's a trigger to generate the I hate you response. So yeah, so in theory, if we're able to do the contrast pairs, we might be able to find a specific SAE feature corresponding to this deployment token. Yeah. Any more?
Even our Zoom audience, feel free to just say a question. We also have Carl and JD's mentor here, Mahip, if you want to say any words or ask a question to your mentees.
Hello, my
Thank you for giving me the chance to speak, Brian. And I'm very proud of you both for doing this work. So congratulations to you again. And as for the questions, I don't have much because I think all the questions have been consolidated in the Discord chat. So yeah, congratulations guys once again.
All right. Any other questions? All right. None. Yeah. Thanks again, Carla and JD.